Okay, this is part B for the video 11.1. We're going to start with an important theorem. I'm going to call it the star theorem because we're going to refer to it later a lot. It starts like this. If the limit of absolute value a sub n is 0, then the limit of a sub n is also 0 when n goes to infinity. So very short, very important. Example, find the limit of n over n plus 1 when n goes to infinity. So we're going to use a method familiar from Calc 1 when we found limits at infinity. We're going to divide the numerator and denominator by the highest power of n in the denominator, and then use the limit laws. So we're going to divide numerator and denominator by n. In this case, that's the highest power, and then use the limit laws. So we have limit n over n plus 1, n goes to infinity. We're dividing by n, the top and the bottom. I'll do that individually. And then simplify. So we have 1 over 1 plus 1 over n, and we know that this limit goes to 0. So what we have left is just 1. So we use the fact, or a formula, we know from Calc 1, that the limit of 1 over n to the r power, n goes to infinity, that limit is 0 if r, the power r, is positive. Another example, find the limit of ln n, natural log of n over n goes to infinity. So we have indeterminate form, infinity over infinity. But that was for functions. So L'Hopital rule is for functions, not sequences. L'Hopital rule for indeterminate forms is for functions, not sequences. So can we really use it? Well, we have a gateway here. We can say, but f of x is equal to ln x over x. Now this is a function, so you're gonna use this rule as a function, ln x over x goes to infinity, so that is indeterminate form. So we're gonna use the L'Hopital rule and find the limit of the derivative ln x, which is 1 over x, derivative of x is 1, and that is equal to, let's simplify it, 1 over x goes to infinity, that is equal to 0. So by theorem, previous theorem that we did in part A, and I will write that theorem right here, it says that if the limit of f of x is equal to L, x goes to infinity, f of n is a sub n is an integer, then the limit of a sub n is also L. And we don't have to have x goes to infinity here. X can go to a number as well, or infinity. So this is the theorem we're going to use that provides the connection between functions and what we know for functions and sequences. So that by theorem, we have that the limit of ln n over n when n goes to infinity is 0. Example, determine whether the sequence a sub n equals -1 to a power n is convergent or divergent. So that sequence, let's list it with its elements. If n equals 1, we have -1. If n equals 2, you get 1. N equals 3, -1. N equals 4, 1, and so on. It's alternating sequence. If you want to graph it so we can demonstrate the elements here, so this is n, and this is a sub n. So the first element is -1. So if n equals 1, we have -1. If n equals 2, you have 1. N equals 3, -1. As you can see, it alternates. Okay, so it oscillates between 1 and -1. So obviously, the limit does not exist. And this is divergent. Example, evaluate the limit -1 to the nth over n. N goes to infinity if it exists. So we're going to take the limit of the absolute value of this same sequence instead, because that was a theorem star. Theorem star, we're going to use this right here. So I'm going to highlight it. We're going to come back to this term over and over. So especially if a sequence has alternating signs, this is very important to keep in mind. You take the absolute value and see if the limit is 0. So that's what we're going to do. We're taking the absolute value, and that is equal to the limit of 1 over n. Now, n is positive, so we don't need absolute value. So an absolute value of a negative number is positive, so we have 1 over n. We already know that this limit is 0. So by theorem star that I just highlighted, we have that the limit of -1 to the n over n is also 0. So let's show the picture for this sequence here. So the picture here, if the x-axis is n and the y-axis is a sub n, we can demonstrate the elements. They have alternating signs. So if n equals 1, we have -1 right here. If n equals 2, we have positive 1/2. If n equals 3 is -1/3. So even though they oscillate, they go positive, negative, but they are getting closer and closer to 0. Another example, discuss the convergence of the sequence. A sub n equals n factorial over n to the nth power. So this general term here, I'll write it again, n factorial over n to the nth power. Let's just remind what factorial is. That is the product of all numbers times 3 times 4 times n. So we see we have indeterminate form, infinity over infinity. We cannot use L'Hopital this time. Cannot use L'Hopital because f of x equals x factorial, this function. If we write the sequence as a function, then we end up with x factorial, but this is not defined for x non-integer. In other words, it's only defined for integers. So we cannot have a function that's not defined for every real number. So let's look at that sequence and list all the elements. A sub 1 is equal to 1 factorial over 1 to the 1. A sub 2 is equal to 1 times 2 over 2 times 2, which is 1/2. A sub 3 is equal to 1 times 2 times 3 over 3 times 3 times 3, and that is equal to, cancel the 3's, it's equal to 2 9's, and so on. We observe that this is decreasing. Observe that the sequence is decreasing. So perhaps goes to 0. I'm putting a question mark. We don't know that. So let's explore this and look at the nth term. A sub n is n factorial over n to the nth power. And let's write this all out. That is 1 times 2 times 3 times n, and n times n times n times n. Now, if I factor out n on the denominator, and on the top, what's left is 2 times 3. I can put a 1 here, but that wouldn't make a difference. And then the product till n. And underneath, I have n times n of them. Now, you notice, I wish I have room here, but I'm going to write this down. I'm going to write that this is less or equal than 1 over n. So note that the numerator is less or equal than the denominator. So just pay attention. 2 is less than n, 3 is less than n, and so on. The numerator is less or equal than denominator. Okay, so we have this inequality. Now, we know about the sequence 1 over n. So we have our sequence, a sub n, that is less or equal than 1 over n, but it's also positive. In fact, this is strictly less. So, if you remember the squeeze theorem, we found 2 sequences, and both of those go to 0 when n goes to infinity. So our sequence is squeezed between them. So by the squeeze or the sandwich theorem, our sequence a sub n goes to 0. So therefore, it's convergent. Another example. For r equals what? The sequence r to the nth power is convergent. So we're going to make a little side note about functions. We know that f of x equals a to the x, a greater than 1. For this function, the limit of a to the x when x goes to infinity is infinity. So let's recall the picture for the exponential function here. This is the case when the base is greater than 1. A is greater than 1. It goes to infinity, okay? Now, if a is less than 1, so the limit of a to the x when x goes to infinity, but a is between 0 and 1, this limit is 0. And we know that as well from the exponential function when the base is between 0 and 1. Okay, so we know this for functions, and we're going to try to apply this for sequences. So the limit of r to the n when n goes to infinity can be either infinity if r is greater than 1. Think about r as our base. So r in our sequence is the base as it was in the function. And it's 0, this limit is 0 if r, or the base, is between 0 and 1. So we need to look at the other cases. So that's clear. Case when the base r is 1. What do we have? Well, we have a limit of 1 to a power n goes to infinity. So that is a limit of 1, which is 1. So it is a constant, 1, 1, 1, 1, 1. So its convergent goes to 1. Case r equals to 0. The limit of 0 to the n is the limit of 0, which is 0. So in this case, we have convergent sequence. The limit is a number. Now, if r is between -1 and 0, so it's negative, then the absolute value of r is between 0 and 1. So the limit of absolute value r to the n, we're using that star theorem again, is equal to the limit absolute value of r, n can go outside, and that is equal to 0. So we use this by theorem star. We can say that the limit of r to the n is 0. Okay. Now, another case, and that is if r is less or equal than -1, then our sequence r to the n diverges. We can see that from a picture. So I'm going to demonstrate those cases here. On the x-axis is n, and on the y-axis a sub n, a sub n. So let's look at the case when r equals 1. If r equals 1, and 1 is right here, our sequence looks like that. It's like a constant. That's r equals 1, and it's convergent. The case when r is positive but less than 1, we have this picture where the elements get closer and closer to 0. So this is the case 0 less than or less than 1, and this sequence is convergent. And so is the blue one. Okay, so now if this is 1 here in another graph, I'm going to illustrate the case when r is between -1 and 0. So we showed that this limit is 0, and the elements will start with -1, and then they'll be positive, and then negative, positive, negative, oscillating, but getting closer and closer to 0. So this is convergent, that case. And the case when r is less than -1, then the elements are going further apart. R is less than -1, and this is a divergent case. And one more picture. N, a sub n, and this is when r equals 1. So this is 1. I'm sorry, this is the case when r equals -1. If r equals -1, our sequence becomes -1 to the nth power. So it will oscillate. First will be negative, and then will be positive, and then negative again and positive. So it oscillates, but it continues to be quite far from any fixed number. So this is divergent. I can also write this case is -1 to the nth power, and it can equal to 1 or -1. So it's divergent because it oscillates and it doesn't get any closer. So summary of all these cases. The sequence, as you can say, it's a very popular sequence. The sequence r to the n is convergent if -1 less than or less or equal than 1. That's important. R can equal to 1 and you get convergent, but if it's -1, you get divergent. We saw this from the picture here. And so this sequence is convergent for r between -1 and 1 or equal to 1, and divergent for all other cases or values. The limit. So when it's convergent, we have a limit. The limit of r to the n goes to infinity is equal to 0. If -1 is less than or less than 1, that reminds you of a geometric sequence, infinite geometric sequence. And it's equal to 1 if r is 1. So a few more definitions here for sequences. A definition, a sequence is increasing. A sequence, a sub n, is increasing if a sub n is less than a sub n plus 1 for all n greater or equal than 1. That is a sub 1 less than a sub 2 less than a sub 3, and so on. It is called decreasing if a sub n is greater than a sub n plus 1 for n greater or equal than 1, for every n. A sequence is monotonic if it is either increasing or decreasing. Okay, so a sequence is increasing if the elements are in order, in increasing order, and it is decreasing if they're decreasing, the elements, all of them. We say a sequence is monotonic when it's either increasing or decreasing. So example, show that the sequence 3 over n plus 5 is decreasing. So we take the first element, the nth element. This is the nth element. Then we take the next one, the n plus 1 elements. That'll be n plus 5 plus 1, which is 3 over n plus 6, we can clearly see that the first one is bigger, right? Because if the denominator is small, then the fraction is bigger. So we show that for two random consecutive elements, we can say that the nth element is greater than the n plus 1 for every n greater or equal than 1. Therefore, our sequence is decreasing. So use the definition, just compare two consecutive elements. Another example, show that the sequence a sub n equals n over n squared plus 1 is decreasing. We must show that a sub n plus 1 is less than a sub n. So this is according our definition. So decreasing, if I rewrote this inequality reverse, but it means the same thing. The n plus 1 is less than the nth element. So let's write down what's the n plus 1 element. If n equals n plus 1, we have n plus 1 over n plus 1 squared okay, so we need to show that this element, I'm going to write down this is the n plus 1 element, and then we need to show that this element is less than the nth element, which is n over n squared plus 1. Okay, now we have to show that, so we don't know for sure, but we can write that this inequality is equivalent. This inequality that I just wrote is equivalent to if you do cross product and multiply across, we're going to have n plus 1 times n squared plus 1 equals, and I'll put a question mark because we don't know that yet. We're doing just cross multiply n times n plus 1 squared. Okay, so now, is that right? Nope, we have more. Okay, so we have n. I see now I'm missing here another plus 1 here. That's why. N times, let's do this. Let's erase this. Okay. So this is n plus 1 squared plus 1. All right, I'll write it here when it has more room. Now we're gonna FOIL. We have n plus 1 times n squared. This is a question mark here. Okay, it's not a squared. So we can actually FOIL right away. Let's do that. So I have n to the third plus n squared plus 1 less, and we're trying to prove that, question mark, n times n squared plus 2n plus 2. So this is equivalent to n to the third plus n squared plus n plus 1. We're trying to show that this is less than n to the third plus 2n squared plus 2n. So let's move things around, cancel n to the third. There's going to be 1 here less than n squared plus n. So if we prove this, if we show this is true, then this is true, and all of them are true to the end. So since n is greater or equal than 1, then n squared plus n is definitely greater than 1. This is true. Okay, therefore, a sub n plus 1 is less than a sub n, and our sequence a sub n is decreasing. Okay. So that was an example, a couple examples used by, we prove by the definition of increasing or decreasing. Now we need another definition here for a sequence. A sequence, a sub n, is bounded above if there exists a number, we'll call it big M, such that a sub n is less or equal than m for every n greater or equal than 1. So bounded above, if there is a number such that every element in the sequence is less than that number, and it is bounded below if there exists a number, we'll call it little m, such that the little m is less or equal than any element in the sequence, and that's true for every n greater or equal than 1. If it is bounded if the sequence is bounded above and below, that means you have a big M and you have a little m, then the sequence is called bounded. Then this is a bounded sequence. Okay, so we have bounded above if we have a number m such that m is the biggest number, and it's bounded below if there is another number, little m, such that that is the smallest number, smaller than any element in the sequence. All right, example. A sub n equals n. This is the natural numbers. Let's write them down. The sequence is 1, 2, 3, and so on. This sequence obviously is bounded below. Bounded below. By what? By 1, by 0, but not above, because it goes on to infinity. Okay, so it's bounded below, not above, so it is not a bounded sequence. To be a bounded sequence, oops, didn't mean to delete that. To be a bounded sequence, it has to be bounded above and below. Another example, a sub n equals n over n plus 1. Let's list those elements here. If n equals 1, you have 1/2. If n equals 2, 2/3. If n equals 3, 3/4, and so on. All these elements, every single one of them is positive and is less than 1. So this sequence is bounded above and below, bounded above and below. So we have little m and big M, so it's called, so it is bounded. This is a bounded sequence. All right, so we know that not every bounded sequence is convergent. We know that not every bounded sequence is convergent. Okay, Let's look at example for that. A sub n equals -1 to the n. So list those elements. -1, if n equals 1, then 1, -1, and so on. This is bounded because every element is between -1 and 1. Bounded above, bounded below, so it's bounded. But is it convergent? No. But it is divergent because it oscillates, doesn't go to a specific number. So another note is that not every monotonic sequence is convergent either. Okay, so example, a sub n equals n is monotonic. Monotonic means either increasing or decreasing. So this is monotonic, 1, 2, 3, 4, and so on. But the limit of that sequence goes to what? Infinity. So it is divergent. So it's not sufficient to have monotonic only and bounded only. You need both. So I'm going to write here very important conclusion. But if a sequence is bounded and monotonic, then it must be convergent. So two conditions, bounded and monotonic, will guarantee convergence. So to illustrate this with a picture, it will look like this. So the sequence is bounded. Here's M, bounded above. And our elements are monotonic. So they're increasing. So there must be some number L here that are sequence approaches. So if our sequence is bounded, that means bounded for every n and monotonic, in this case is increasing, then the terms of the sequence are forced to approach some number L. And that's our limit. A very important theorem that summarizes this, it's called the monotonic sequence theorem. Monotonic sequence theorem. Very short. It says that every bounded monotonic sequence is convergent. So two conditions, bounded and monotonic. And that concludes the video for 11.1.